Okay. Hi, everyone. Can you guys hear me? Sorry, I think my laptop's being a little slow. Okay, perfect. So let's go ahead and get started. So hi, my name is Anna White. I am in the Masters of Applied Data Science program, and I also work here in the Statistical Consulting Lab. And so today we're going to talk about different methods for missing value imputations. I'm also here with Maria, Janet, and Jonah. So we'll go ahead and get started. This right here is just the Anaconda Cloud. So if you have an account, all you have to do is click Launch Notebook here. Then it'll take you to a page where it says like Start Server or Launch Server, and you'll click on that, and then it'll bring you to this, the Jupyter Lab. And so all you have to do is click over here and press Upload, and you can then upload the notebook I sent earlier today. And so we'll go ahead and get started. This is what it looks like if you're using the cloud version. I have Anaconda downloaded on my laptop, so I prefer this version. So I'm gonna go ahead and use this. So, sorry, welcome to our workshop today for imputation methods for missing data. So real quick about different types of missing data. Really, missing data can occur for probably anything. Sometimes maybe you're running an experiment and somebody forgot to click record on one of your instruments, and then that data's gone, you can't replicate for whatever reason. Or a lot of times, really what it is non-response, or especially in surveys, we see that a lot where people just decline to give answers for any sort of reason. And so, or maybe the data was entered wrong. But besides the point, missing data can occur a lot, and for any sorts of reasons. And really, what we really want to let people know is that dropping data is never going to be the preferred method, even if you're missing a lot of it. A lot of the times what this can do is it can create bias into your estimates, which is not ideal. And it can also hurt the power of any statistical test that you hope to perform. It's going to hurt the power because your sample size is going to be less than what it could be. And so because of that, because we don't want you to drop, but really that's the easiest way. We want to let you know different ways that you can impute values. And this isn't mentioned in here, but this is really important. If you're doing an analysis where you ended up needing to drop, or no, if you're doing an analysis, really, if you're going to impute, what's really helpful is to go ahead and run your model without all the missing data, and then impute your data and run the model again, and then report both results to kind of show maybe how different or alike your results are with those imputed values. So anyway, we're going to go ahead and get started. First, we need to talk about the different mechanisms of missingness, is what we call it. So there's three different ways or manners in which data can be missing. The first one is missing completely at random. And really what this means is that all the missing data is not related to anything observed or unobserved in the data. So when we say observed, we're talking about the variables that you have collected in the information you know that is observed in the data, and unobserved could be for any other outside related reasons that you might not be able to record. So when data is missing completely at random, this means that you assume that the data, there's no pattern or rhyme or reason why anything is missing. So you assume that the data that you do have that is complete is just a random sample, or no, the missing data is a random sample of the complete data. And so next we have missing at random. So this means that the data that is missing can depend on your observed values, but it does not depend on the unobserved values. So what this means is that data that is missing can be explained by something else that is in the data, which might be a little confusing, but once we talk about missing not at random, this will make more sense. But and it's important to note that after you impute data that is missing at random, that imputed data should look very similar to the original data, but it won't look exactly the same while missing completely at random. It should look almost identical. And then finally, we have missing not at random. And this is when missing values occur on something that is unobserved in your data. And so the example I gave was perhaps somebody there's like a simple survey and people are just reporting like what they do, or not what they do, just what their income is and things like that. And maybe somebody makes a lot of money and a lot more than everyone else. And they think that everyone will. My professor gives an example where they were in a class where there was a guy who was, his father was like some really famous golfer who made a lot of money. So he let that one blank because he didn't want people to know how much, but everyone kind of still knew it was him. And so he left it blank because of what the income itself was. So that is considered missing, not at random. And imputing data that is missing, not at random, is hard and not ideal. So the best you can do is look for something that looks plausible, like it makes sense, but you should not expect your imputed data to look exactly like the complete data. And additionally, and we'll get into this later, there is a test you can perform to decide or to figure out whether or not your data is missing completely at random. And so you cannot decide based on just the data itself whether or not it is missing out at random. You have to know more about how this data was collected and who collected it and what they were collecting it on and things like that. And so, like kind of what I've been saying, it's really important to know the mechanism in which your data is missing because this can tell you what kind of different imputation methods you should be using. And so imputation methods, there's a lot of different ones. We're going to show some cool ones and some ones that maybe you should avoid. And especially when you're imputing data, it's very important. Really, what you want and what is most ideal is you want to preserve the distribution of that original complete data that you have. So we're going to show you some ways that you should look at your data before and after imputing and to compare and see how well that imputation worked, maybe how well it did not work. So we're going to go ahead and get started. And real quick, there are some instances, here I'll scroll down and show you, where it says pip install, like right here. This is just because it's probably possible where you don't have this package installed. So you might have to install it first if you're getting errors. And then after you install it, you probably just need to go over here and restart the kernel and then run the cells again. And then you should have no problem. So now that that's out of the way, we can go ahead and get started. So this is just some setup for some packages. And then we're reading in the data that was sent along with this notebook. It's called College Missing. And so this is just a little snapshot of what this data looks like. And also the shape. So this means there's 777 rows or observations and 10 columns. And so it's very important when you're working with data that you know what this data is, even if we're just doing something like this where we're imputing. So real quick, I've got some descriptions here of the different variables. So we've got the school name, whether or not this university is a private institution, the number of student applications they received, the number of students they accepted, the number of students enrolled for that year, and then the average cost of out-of-state tuition per semester, room and board per semester, books per semester, the student faculty ratio, and the graduation rate. Just these are really important. It's just so you know when we're talking about things later on what we are referring to. And so when we're imputing data, the school is basically the ID, and since it's a character or just the ID in general, we don't want that information for imputations because it's not going to make sense and maybe mess something up. And especially with school, it's a string, and so if you try to run imputations on it, it will give you an error anyway. So we're going to go ahead and drop this column. Additionally, private is categorical. You can see here it's yes, that's missing it, not applicable, but anyway. So that means that we need to encode it. It's yes or no. So all the yeses are now ones and the no's are now zeros. And so here, this is what, once I get a data set, and once I know what all the variables mean and I've read it in and I made sure I read it incorrectly, like we have, I like to get a quick description of the data and using this dot describe. And what it's doing, it's giving you how many, then the mean, standard deviation, and then like the 5 numbers. So it's really good to look at a quick glance. And this count is really helpful because we can already tell that there is some data missing here, especially earlier in the shape. Notice that it had 777 rows. And then here, some columns do like enroll, but then notice these 3 at the beginning, they do not. So that is definitely the first indicator that there's something wrong. There's some data missing. And so we can go ahead and investigate this further. So this is just a quick function where we're basically summing up all the null values in this data set and per column for all the columns, and then dividing it by the number of rows. And this is going to give us the percentage of data that is missing for each column. So here, accept has got almost 13%. That's quite a bit. And then applications or apps has about 6%, and then private has like 6.5. And so once you know you have some missing data, the next step is to go ahead and explore and kind of visualize the data that is missing. So this is called a data matrix plot, and all the black area represents observations that are complete, so they are not missing. And all these little lines represent observations that are missing. And so really what we're looking for here is some type of missing data pattern. So what we can tell looking at this is kind of what the proportion told us already, that accept has a lot of data that's missing. Apps has a couple, and private also has a few. And it doesn't look like maybe this observation right here is missing apps and accept, but it doesn't necessarily look like there's a strong pattern where some observations are clearly missing two or missing all three or anything like that. And that's what you're looking for in this kind of plot. And so, yeah, there appears to be no strong patterns in missingness that we should be aware of. And then using this package, missing no, you can actually do this is another way to visualize the proportions per column. So as you can see, this is also going to give us the count, which I find to be really helpful. And then over here, the proportion. So this is just another way to visualize that the accept is missing the most, especially compared to these two who are missing relatively not that much compared to acceptances. And so this is pretty helpful. And so usually the next step after you visualize your data and how it's missing is to run a test. So we're going to do Little's test. And what Little's test is the null hypothesis is that this data is missing completely at random. And the alternative hypothesis is that this data is not missing completely at random. So here we perform the test, and then we got the p-value. And as you can see, this p-value is low. It's less than usually. We'll just go with alpha or significance level of 0.05. So that means that we're going to reject the null, and we're going to conclude that this data is not missing completely at random, which is bad news. Missing completely at random in general is going to be much easier to imputate. And so this is an important step. Like I was saying earlier, we cannot conclude whether or not data is missing not at random using just the data alone, but you can for missing completely at random. So we've concluded that this is not, so this data is either missing at random or missing not at random. We're not sure which one. In order to conclude missing not at random, we would have to know more about this data. But so now we know all of that, and we know what's missing and about how much we're going to start imputing. So first, we wanted to show an example of what would happen if you did, it's called a single value imputation. Single value meaning that we're going to give each missing value the same value per column, which is going to be the mean. So we're going to go ahead and do this. This is just a quick way. We calculated the mean, and then we said for all the missing values in this column, fill it with the mean for this column. And so, and this is for numeric. You cannot do that with categorical. There's no mean, but just for numeric, this is what that describe that like 5-number summary and summary statistics are after. And here's before. So trying to get a real quick snapshot of these. You can tell that these are now complete and that it worked because they're 777 instead of the 731 or 676 before. And so as you can see, the means actually did not change after this imputation. But if you look, standard deviation has gone up for both. And then it looks like the medians have changed for both too. And maybe some other of those quantile, the 25%, 75%, 50% change. So that's a good thing to get started with when you're looking at how well your imputation performed. But we do want to look deeper. So next we're going to look at histograms. So I like these a lot. We'll first look at apps. So here we have before and after imputation. And so notice how this second bar here has gone definitely increased for this histogram after imputation, but everything else has stayed the same. So that it's not usually what we want to see, and for accept, the same thing has happened. And so this has happened because how a histogram works is there's these different bins based on it's the count of how many values occur in this range. So because this is where the mean is, that bin has increased while all the others have stayed the same. And this is not ideal because this means that the distribution of the data is not being preserved, which is the exact opposite of what we want. And so really what we're just trying to say is that the single mean imputation is not ideal. It's going to change your data, which you do not want. So another way you can look at this too is look at correlations between your variables before and after. So this is for what we've imputed for numeric. So absent except before imputation. Then here we have after. Trying to see if I can have these both in. Okay, it's kind of hard to see, but we do have apps before and after, and it does look like, especially right here, that correlation has changed. And yeah, what you're doing is basically looking for this row up here and down here. Has it changed? It's changed a little bit for some values. And then for accept, yes, it has changed. Specifically, the correlation between absent and accept has changed. But if you go further down, there are some changes as well, which is not really what we want to see. So they might not be drastic, but the distribution of this data was still changed, and that is not ideal. That is not a good way to impute data. So now that we've kind of shown what is not a good way to impute data, what is a good way? So really, what is a good way is going to be MICE imputation. So MICE stands for multiple imputation by change. I believe this is supposed to be change, not change, but that's okay. Chain equations. So what MICE does is it's going to, based on the relationships between variables in your data, it is going to essentially, depending on the type of data, so for numeric, it's usually going to default to linear regression, or for categorical, it'll default to logistic regression. So what it's going to do is going to predict the column that you have missing using the information it has from the other variables. It's going to basically perform a model to predict those missing values. I mean, it's not going to do this once. It's called multiple imputation. It's going to do this a couple times and then decide which data set works the best that it has generated. And so this is relatively easy. A simple way to do this is actually just using from this library FancyPute, the iterative imputer. And so here we're only going to do numeric, like we've been talking about. So we're going to drop that private. It's going to think it's numeric instead of categorical and then mess it up. So we're going to leave it out and then do the iterative imputer. The default is linear regression. So we're going to do that for this missing data. And so this is before and after imputation. And so as you see, the mean has changed now, unlike the last one. And then we're seeing a decrease in standard deviation, which is what you should be seeing or what you can expect to see after imputation most of the time. And then here we have those different quartiles. Some of them do look like they have changed. But what about the distributions of the data? So we go look, this is for apps. As you can see, this second bar did not go up like it did last time. And so it's definitely increased. Like this top bar went from probably around 475 to almost or a little bit over 500. So these bars have changed, but relative to one another, these look the same. And that is what you want to see. That means that the data distribution has been preserved. So for apps, yeah, you can see just about the same thing, that this data distribution has been preserved after imputation. And so if we go look at correlations now, okay, for apps, starting here, yep, these do look, once we get out here, they do look a little changed, but they're mostly similar. And for accept, same thing. This one has changed, but for the most part, these are once again mostly similar. And overall, while the correlations don't look exactly the same, the distribution looks far better than that for single imputation. And so while this has been a more traditional statistical approach, next Maria's gonna talk to us about KNN imputation and some more machine learning methods that you can use that might perform better than even traditional statistical methods.
All right, thank you, Anna. And hi, everyone. So now I'm going to take it from here and I'm going to talk a little bit about KNN imputation, which is another method that we can use to impute. And like Anna was saying, like MICE imputation tries to predict a value based on the other features that we have. KNN does basically the same thing. It learns from the other data points and it tries to look at the nearest neighbors. So it looks to the observations that resemble the most in terms of the values that are not missing, if that makes sense. If you're familiar with the KNN for modeling, it's pretty much the same thing, just like instead of modeling something, you are putting it into a value that is missing. And one thing that is very important for this type of imputation is that it's relying on distance from whatever observation to another. So one thing that we really need to do here is scale the data. In our example here, we use the standard scalar, which is the mean over the observation minus the mean over the standard deviation. And then we can convert it back to make sure that the imputed data is not going to be scaled, because if not, it wouldn't make sense. But this code that we provide here does everything for us. And then we just get to run that. And we're using 3 neighbors here, but we can also change that, and we can use like as many observations as we want to try to find which is the most similar one and try to predict something. And then we can do the exact same process that we were doing before. We're going to look at the summary statistics. We can look, for example, the mean. We see again that they decreased a little bit, but since the data, the missing data pattern is not missing completely at random, like Anna was saying in the very beginning, in which like they should look almost exactly the same. This is not super concerning because we know that this is not the missing data pattern in our case. And in terms of the standard deviation, they are a little bit lower, but not so much considering the magnitude. So that's also a very good thing about this imputation. All right. And then we can also see what happened to the plots like we were doing before. And in this case, we can observe something very similar to what was happening with the mice imputation, in which the overall shape has been preserved, although we can see that some of the bars are a little bit higher right now, which is totally normal because we are adding more observations to the data, right? And that's for apps. And then when we go to accept, it's pretty much the same thing. We can see that most of the values were imputed between that in that first interval. So that's why we see like the biggest increase there, but the overall shape, it's all right. Okay, so then we can also see how the correlations look, because the point of looking at the correlations is trying to see if the relationships between the variables were preserved. And this is like, if you are imputing this for creating maybe a model or something like that, you really don't want to mess up those relationships. So this is something very important that we need to look at. And if we look like compared to the other methods, this one look a little bit closer. If we see the ones that we are imputing, which is apps and accept, go from 0.95 to 0.94. So it's pretty decent. And so the other ones also look pretty much the same. So we're basically looking at values. We want to see something similar. So that's another method that we can use. But one thing that I do want to mention is that unlike the mean that Anna was saying earlier, this one, the mean obviously you cannot use for categorical data, but KNN you can, because you're going to look at variables or values that okay, so which one is the most alike, and then maybe you can predict the class or the category to what it belongs based on something else. So that's what we do here with KNN. But before, like we did in the very beginning, we're going to show you a way that is not probably the best. So for categorical imputations, a popular way, and probably like the easiest one, is just to impute the most frequent value. So it's like a mode imputation. So just because like maybe the higher chance, what is like this missing value, which category is the most likely going to belong to? And obviously we're gonna say, all right, so the one that has the most values belong to, right? But this is not really logical, because what is the chances also that all of the values that are missing belong to the exact same category, which is also the one that is repeated the most, which might not even mean that it is like the one that is repeated the most. If we have like a lot of categories, might not even reach like half of the observations or things like that. So this is kind of dangerous to do, because we can alter these relationships between the variables. And here we can see a little bit of that when we're looking at the proportions of the variables here in the data. We see that private, we had yes or no for whether the institution is private or no. And we have 72% that were private and 27% that were not. But then we look after an imputation and we see that 74% now are private and 25% are not. And we can argue that these are really close, but this is because this variable was not missing a lot of data. So as long as you don't have a lot of data missing, this could be something acceptable, though not the best option. So that's why we're going to show you a new one. But when you have a lot of missing data in a categorical variable, you definitely don't want to use this method. And then, like I was saying before, KNN, one of the advantages over some other methods is that it also works for categorical data. So it's basically doing the same thing that we were doing before. Instead of looking for the closest number, now it's gonna look for the closest ones in terms of a category. So we're looking, oh, which ones are the more like to this one? So we can say, oh, maybe it belongs to that. And now we can see that our percentages belonging to private or no went from 72 to 72.8, so 72.3 to 72.8, which is even closer than what we were observing before, and from 27.68 to 27.16 or 155. So yeah, those are really pretty close, and it's like a little bit more reliable than just imputing the one that is repeated the most. And probably this is the last method that we wanted to share with you today. And here you can see another time if you're running this with us, most likely you're not going to have this package installed, so you're probably going to have to run that cell. But basically what mice forest imputation does is like a mice imputation, like the one Anna was talking about earlier, though instead of using linear regression or logistic regression, so trying to find like a linear combination of the variables that are present, what this is doing, it's using a random forest to impute this data. And if you're familiar with modeling, you know that sometimes this random forest for modeling tend to work a little bit better than linear regression in some cases. So for imputation, there were some articles and stuff that they were saying that this was a little bit more reliable, though it always depends on the data. So it's really something like to be careful about, but we still wanted to show you because we thought this one was pretty interesting to include. So yeah, Mice Forest is the name of the module that we are using here, and it has like a lot of applications. So we actually included the link where if you're interested in this method, you can research more or maybe contact us later as well. But to briefly show you what you can have to do here is we are using the kernel method in this workshop. And for this one, we first have to state what data we want to impute, how many data sets we want to create, and then it's going to create kind of like a pool and take some criterion to choose what is the best imputed value for the ones that are missing. So maybe it's going to create 4 values that could be suitable for that value that it is missing, and then either it picks one at random, or it can take the mean of those 4 to impute it, or things like that, or the most repeated one if it's a categorical, things like that. But it depends, and this can be edited and manipulated depending on what you feel it's better for your own data. So yeah, once we select the kernel, we can even print it and try to see yeah, how it looks like. We can see how many samples we have in our data, how many columns, how many number of variables. And then like mice, this is an iterative approach. So we can tell Python to run it as many times as we want. And here we're running it just 2 times. And then very simply, we can use the kernel.complete data to complete the data set and just impute the values that were missing, and then it's going to be up to us to try to see if the imputation was good or no. So we can go and try to see now, okay, we don't have any more missing values in our data, which is great, and we can compare again the summary statistics and the plots that we were looking at. So here we can see so for the mean, it's looking they are pretty close, right? I would say like maybe even closer than the method before. And so is the standard deviation. I think it's the closest one of all of the ones that we've seen. So in cases in which your missing data pattern is missing completely at random, this is particularly useful because as you can see, the nature of this is like it preserves it really well. But it does work. It's very versatile. So it does work with other missing data patterns and yeah. So going to see the histograms, we're observing similar things than before, in which like maybe the bars increased a little bit, but the overall shape is the same. What we don't want to observe is something crazy, like something totally different than what we're observing before. So here for apps, and we're looking at that pattern, and for accept, again, we observe that they are pretty similar. So this is very good. And lastly, we can even look at the correlations as well again, which like at this point, I'm sure everybody is familiar now with how the correlations are looking, but like look at this method, APS and accept, where had a correlation coefficient of 0.95. And after this imputation, it's the same, it's still 0.95. So the relationship between these two has been preserved really well, and the other correlations are pretty similar. So we have preserved the nature of the data while doing this. And now this method, like we were saying, it also works for categorical data. So we can go ahead and look at the proportions. And as you can see, we started with private institutions being 72.3% of the data, while non-private institutions were 27 point about 7% of the data. And right now we have 73% being private and 26.9% not being private, which is still a pretty close value. And since like the data that is missing, we didn't observe it, there's no really hard truth on what is good or what is not good. But yeah, so basically here in the bottom is the link that I was referring to earlier, where you can see like different classes that you can apply for this method and different changes and adjustments that you can make if you're interested. It's a really good tutorial. It goes step by step. So like as supplemental material, we thought it was really good. And that is kind of like what we wanted to show you as an overview of how you could impute some data. And mostly these methods work for regular tabular data. You know, once you have put it into your spreadsheet or a CSV file or stuff like that. So yeah, Anna, I don't know if you want to jump with some conclusions or something.
Yeah, thank you, Maria. That was really good. So, yeah, as just as what we've been saying, please consider imputation instead of just dropping any data that you have missing. And like I kind of said earlier, but especially if you're doing an analysis, don't be afraid to drop the data that's missing, report your analysis, but also impute and report again. I find that those results to be a little bit more reliable from the researcher and also to be helpful and can kind of come in and try to say maybe parts of your study that because you're seeing a lot of data, so you can have maybe more to say about whatever you're researching. And also don't be afraid to go beyond the traditional statistical methods like mice. As we've shown, it's things like the mice forest or even the canine imputer are very promising. So don't be afraid to try a couple things and just be sure to analyze before and after of your results to see maybe the invitation did not work very well. And if not, you need to find a better method. So, but yeah, I think that's all we have. Does anyone have any questions about anything that we talked about or about any of your own data with missing values?
Um, I got a quick question if you can hear me.
Yeah.
All right, and thank you very much for your presentation. Question that I have is obviously is about imputation, and clearly it's the best to have the actual data, but when you have missing data, it's suboptimal. Is there a point or is there a cutoff point at which you would say, well, I think you're missing too much of a data, really. Imputation probably would be a no-go in this scenario. Maybe the best is to just drop out that variable and forget it altogether. Is there a cutoff point, or is it just kind of really depending on the nature of it, and if you're not changing the relationship of that variable with others, you'd be still fine to imputate, let's say, 30% of the data?
Yeah, that's a really good question. Thank you. And it's definitely one of those things where in statistics, nothing is really cut and dry, and everything always depends on the situation of what you're doing. I will say if you're doing a study and you're finding that like you have so much data that you're not really going to have enough or big enough sample size to really make any conclusions, or kind of get out of jail free card is that's just a pilot study. So you don't have enough information to really answer the questions you want to answer, which obviously sucks and is not ideal, especially depending on the time, effort, and money put into it. I will say, depending on the observations themselves, you should be careful. Like sometimes maybe you have quite not a lot of data missing per each column, but maybe there's a couple observations that are missing most of the columns, or maybe they're missing too much to a point where you feel like imputation is really just pulling something out of nowhere. Then I would definitely drop I think it's just important to report what you're doing and why. And if you're unsure, definitely find someone who's maybe an expert in the domain that you're doing, or even just like someone who's very statistically advanced, or like the lab, or you could come to us and say, well, do you think this is okay to drop this or not? And we will do our best. But yeah, you're right. It's definitely a judgment call, and there's no percentage or cut and dry, cut off, yes or no, you can drop this, or you have to impute or anything like that. I hope that answers your question.
Yeah, and if I can add something to the answer, sometimes it also depends on how many observations you have in your data. Because if you're talking about something where you have like hundreds of thousands of observations, maybe 30% missing, given that you have such a large number of data that you're not missing and you have there, maybe it's not that much, and you still have enough information to do that imputation. However, if your data set is small, then we're looking at a different thing. So it also depends, and we have to be mindful of how many observations you do have in your data to try to like deal with these percentages. So it's a combination of everything, I would say. And then yeah, thank you. And then also it would also depend, I guess, like if your variable is like what you observe on that variable, like if it's something that is very unusual, you have a categorical variable, like I don't know, blood types, and there is a definite pattern of how the distribution of the population. So in general, like if your sample is representative of all of the people, there are studies that can tell you like, okay, about this number of like people or percentage of people should have this blood type or stuff like that. So then that's something that you can compare to other studies done in the past or stuff like that. So it really depends on the data set, but I would say, yeah, definitely look at how many observations you do have, so your sample size, and then maybe like what has been done in the past, and yeah, go from there.
Great. Any other questions? Okay, real quick, I just want to say we do have a survey. Oh, this is big. If anyone wants to do us a favor, definitely optional. You want to leave us any feedback, and there's also an option to maybe request future workshops or anything like that. You can definitely go ahead and do that. Let's see in the chat. Yeah, if you would like the recording to be emailed to you, you can just go ahead and email the Statistical Consulting Lab's email, the scl@etc.edu, and just say, I'd like a recording of the workshop, and we will send it to you. Okay. Does anyone have any final questions or comments? Yeah. Stop sharing, but thank you guys so much. If anyone has any other questions or about missing data or anything like that, you can definitely feel free to email us at the SCL email. And so we'll probably just stay on for a couple of minutes, but I hope everyone has a great day. Thank you.
Thank you.